This is section 6.3 on 802.11 wireless Wi-Fi. These are four 802.11 protocols that have been defined and standardized. You know these letters, right? 802.11b, A, G, and N. All these protocols are wireless protocols that allow for wireless local area networks. They all use CSMA, collision avoidance, for multiple access. So this is the random access type of scenario. We'll see that all these are really, in some way, sort of an extension of wired Ethernet. They use a lot of common structure. Notice for each of the protocols here that are listed out, you can see the spectrum that they use, whether they're in the 2.4 gigahertz or the 5 gigahertz spectrum. So that's actually the frequency at which the signals are operating, travel at. You can see the speeds that are achievable over all these. 11 for B, B's pretty old now, and 54 for G, up to 200 megabits for N. Also, all four of these have traditional infrastructure mode, like we talked about last time, where there's a very clear base station and or access point, and then there are the mobile hosts, but one guy is kind of in charge and is connected to a wired network. There are also ad hoc versions of these protocols, meaning they support just point-to-point connections between different computers. So there's no access point involved. You could talk directly to computers. This is sort of the terminology that's used in 802.11, where you've got a base station or an access point. Instead of having cells, like what we call them cells in the cellular networks, we have a basic service set, a BSS. So that's kind of a grouping around an access point. The host associated with that. Note that the access points are going to be connected to some other kind of wired switch or hub or router that's going to do the things that we talked about in the previous chapter. But still, this is an extension of the link layer. All right, so 802.11 is a link layer protocol. 802.11 uses channels and association. These are two important terms. What are channels? Well, these are the way that the spectrum is divided into different frequencies, and that's based on the frequency. So this is like a frequency division multiplexing, where we divide the spectrum between 2.4 gigahertz and this 2.485 into 11 different channels, which are going to be a certain kind of bandwidth wide. Those frequencies can be set by the administrator of the access point. There are 11 possible channels, but I think there's only 3 non-overlapping channels. Basically, channels 1 and 2 kind of partially overlap, so you interfere with each other if you're on those 2 different channels. Now, I think if you do 1, 6, and 11, they don't overlap. So interference is definitely very possible in this 2.4 gigahertz range. And it's also at the other one, but you can set your router to different channels to avoid interference. Have y'all had this issue before? It'll happen if you got a lot of routers in near proximity to each other, because if you're on the same channel, then even though you're kind of a part of 2 different BSSs, those kind of cells, right? If you're associated with one access point or the other, your signals are going to be interfering with each other, and that's going to hurt your routers out of the dorm, isn't it? I bet it is, yeah.
I think the experience like this was, I shared my dorm room. My dorm room was at the far end of Benton, so at the sports center side, and my room was just no Wi-Fi at all. And eventually, the networks people like Greg and Tim came and looked, and what it was is right at my room was the interference between the Science Center's router on that side and Sports Center's router. So
Science Center router is reaching all the way over there?
Yeah,
I believe it.
Benson.
No. But to the other side of Benson?
Like right there. And so they said what was happening is like I guess this is what this was experienced like. The kind of routers they were using, they would call them smart routers, and they said that they were like seeing each other and they were on the same channel. So they were telling, like one router was telling the other router, "It's okay, I got this guy," but the router was also telling the other guy, "It's okay, I got this guy." So nobody was like covering that spot. So was that an experience? Like, was this like?
I mean, it's associated, I guess, with this, but it's at a kind of higher level. If these routers have some intelligence about how they're accepting, or this association is the technical word for what's going on when a host decides to be connected with a certain access point. And it does that by sending out, basically doing some scanning, where your computer might send out a frame and say, "Hey, who wants to pick me up?" And then the routers would reply back, and then you might pick the one that has the highest signal strength. It looks like in this case the routers were smart enough that they were even talking among themselves because they were actually linked together because they're all belonging to Freed, to try to make that association even smarter from a global perspective. This association is just a way for hosts to select an access point to be connected with. Typically, you're also going to do that access point is going to run DHCP so that you can get your network address, and it may perform authentication like the new routers, right? The FHU Secure is going to also perform authentication. This is the two types of scanning. Scanning is the process that's going to allow us to associate with an access point. There's passive scanning. In passive scanning, the access points send out frames, beacon frames, periodically. And when a host receives one or multiple, then it would say, "Hey, well, I got a probe frame, a beacon frame from AP1. I got another one from AP2. It looks like from signal strength that AP1 is a lot better, so I'm going to connect with him." And in response to that, the host would send an association request frame to access point 1, and then that access point would send back an association response. So these are special kind of frames that signal to both parties, this is what's going on. Notice when this guy associates with AP1, the access point 2 would also learn about his presence because he would receive that association frame as well, but it wouldn't be addressed to him. So in passive scanning, the host doesn't have to send anything. He just receives stuff. Right? Active is kind of when you want to be more proactive about it and say, "Hey," in this case, the probe request frame is sent from the host, so the mobile host actually initiates an association request to be sent back to them from any route or any access points that can hear it. So it's active or passive from the standpoint of the mobile host. Does that make sense? Whether you just listen and passively choose one, or if you kind of request to get offers from different access points. As I said, we're going to use CSMA-CA, where the CA stands for collision avoidance. We will sense before transmitting so that we don't start transmitting if somebody else is transmitting. However, we're going to do collision avoidance instead of collision detection. Remember CD. This CD is what Ethernet does. The reason that we don't do collision detection is that it's difficult to sense collisions when you're transmitting due to the way signals fade or the signals get smaller in wireless. So it would be difficult to hear that somebody else is transmitting at the same time you are because you're screaming so loud you can't hear the whisper of that guy's signals. Also, as we looked at last time, you can't sense all collisions anyway because of the hidden terminal problem. That is, if you've got one guy who's in the middle of two, but these two can't talk to each other, can't hear each other, you could still have collisions in that case. How does CSMA-CA work? Here's kind of an overview. The idea is that we're going to define this quantity of time called diffs. And you're going to listen for a diffs period of time. And if you don't hear anybody transmitting for that period of time, you send your frame, your whole frame, and you don't stop because you're not doing collision detection. All right, so this is what happens. On the other end, the receiver will send back an acknowledgement after a SIFS period of time, which this is a SIFS is short. That's what the S stands for, so it's a shorter period of time. You'll get back an ACK. So this, if you get the acknowledgement back, then you know that your frame actually got through. What do you do if the channel is idle? No, if the channel is busy, that is. So you wait for diffs, and during that diffs period, if you sense that the channel is busy, then you're going to do something kind of like what Ethernet did and start a random back-off timer. You remember where you choose a random number between this number and this number, where that's based on the number of times that you've had collisions. But the difference here is that the timer counts down only when when the channel is idle. So this is CSMA-CA, and the big differences here are we don't do collision detection. We send the whole packet after we've waited our time period. This time period is initially going to be diffs, but it may be longer if we have if the channel is busy when we sense it initially. If it is longer, we're going to kind of choose a random back off time, and we're only going to back off when the channel is idle. What these mechanisms do is they decrease the chance that there's ever a collision. Okay. 802.11 incorporates one other mechanism to avoid collisions, and it's called request to send, clear to send. And this is used, it's optional, it can or it doesn't have to be used, and generally it's used if the data packets are a certain length, if they're large, above some threshold. What they do is they allow the sender to reserve the channel so that there's no collisions during long packets, which would be more wasteful. The idea is if we wanted to talk to each other, we would say, hey, I want to talk to Lance for 3 seconds. And Lance would yell back, okay, you can talk to me for 3 seconds. Since we yelled, everybody else in the room has heard that, and don't talk for 3 seconds because there's already been a request to send and a clear to send message that came back. Right, that's basically what this thing says. Here's a picture of it. So imagine we've got A and B with the access point in the middle. A and B cannot hear each other because they're too far away from each other. But if they both talk at the same time, they're gonna overlap and collide at the access point. So what A would do here, or imagine A and B both want to talk. A and B both send an RTS, a request to send, and there's a collision. Now luckily, there's just a collision in the RTS packet, which is small, and so we didn't waste that much time. We didn't actually collide real data. So in response to that, because we didn't get a clear to send back, there'll be a random back off once again, and then a resending of the RTS packet. Imagine that A sends his first, his RTS here, and it does get through to the access point. In response to that, the access point is going to send back, okay, A, you're clear to send, and you can have 500 milliseconds or whatever time. Actually, this time would have been in the request to send, a duration of time that it's requesting, kind of reserving. In response to that, here's the beauty of it, right? If the access point sends a clear to send, A gets it, but B also gets it. And since B now knows the situation, it will respect that reservation and defer that period of time over which this large data packet is going to be sent. After the data packet's sent, an acknowledgement is sent out, and you can see here now B knows that this transmission is over because it's received an acknowledgement from A. Does this RTS CTS thing make sense? Any questions? I think it's a pretty elegant solution to this problem of how do you let people that you can't even talk to know that you're about to talk, right? And that's what both of these messages do. Here's a look at the 802.11 frame. So this is the way it's broken down. Those numbers across the top represent the number of bytes in each field. You can see this duration. That's what I was just talking about, where this is how long you expect your packet to take. The payload, that's the actual data that we're sending. CRC, we know what that is, the cyclic redundancy check, right? So we're doing error detection. The interesting part here is the 4 addresses, right? This is huge. How many addresses does an Ethernet frame have? You remember? It's less than 4. 2, right? What are the 2?
Source and destination.
Right, just sender, receiver, source, destination. In the case of 802.11, we actually need 3 or 4. The 4th, as it says, is only used in ad hoc mode. We're not talking about that. And they can actually, the purposes of these might change. In our traditional infrastructure mode, we need the extra one. I guess the long and short of it is we need the extra one because we need also the MAC address of the router that we're sending this to, which the router may be a different computer, have a different address, MAC address, than the access point. Whereas the address 1 is the MAC address of the host or the access point to receive the frame. Address 2 is the MAC address of the host or the access point transmitting the frame. And then 3 holds the router. And here's a picture of that, basically showing you here that when you've got a host, an access point, and a router, the access point is really a link layer device. Right? It doesn't know anything about IP addresses. The router does IP address, network layer stuff. And to the router, all these hosts are connected. Right? All these MAC addresses are connected to it. As in, like, sort of, they would look like they're directly connected to it. Whereas, in actuality, that is being provided by the access point that's going to translate or convert the 802.11 packet frames into Ethernet 802.3 frames that just have the 2 addresses. And to do that conversion, it needs those 3 address fields. I think there's so in this case, if we're sending a packet from the host 1 to the access point, and address 1 is the sort of the first destination, the access point's MAC address. The second one is like our source, which is the host 1. And then address 3 is the MAC address of the router, which is it's kind of like another destination for this datagram, right? That's where it really has to go after it goes through the access point. So that's why we need the 3rd address, is because really we've extended the link layer to involve this 3rd party, the access point, instead of being directly connected to the router. You will notice if you look at it here, these are 6-byte addresses. 6 times 8 is 48. 48-bit MAC address is exactly the same number as we had in Ethernet. So they're the same kind of MAC addresses. They're compatible. This shows you the rest of this, the way the router is, the access point is actually going to convert this to an 802.3, a regular Ethernet that has the router's MAC address as the destination and the host as the source. So it kind of removes the access point from this system. All right, here's the rest of this. This isn't super interesting, but just shows you the rest. This frame control is where a lot of the protocol is defined. That is, what's the version, what type of packet is this? Is it a RTS, CTS, an acknowledgement, or a data? What kind of packet or frame? As well as a bunch of other stuff here. These are in bits, these numbers, and these are in bytes. That's why you can fit all these numbers inside of a 2, right? Because it's really 16. How does mobility work when you move within the same subnet? So if imagine we've got this scenario where there's a router connected to a switch, and the switch is connected to 2 access points, right? We have this host that's in the, this should be BSS, I'm sorry, BSS1, and it moves over to BSS2, basically the the range of one router, the range of one access point to another access point. So what's going to happen here? How does the switch here know to start sending packets that are addressed to the MAC address of H1? How does it know to send it to access point 2 instead of access point 1? That's kind of the question. Does that make sense to you? So when it's going to have to change the link layer switching, the switching table, so that the packets get sent here. And the answer is we're going to use the self-learning property of the switch. And typically, we're probably going to broadcast a packet on this network saying, broadcast a packet from H1 so that the switch can learn that this MAC address, H1, is now on this access point instead of this one. All right, note this though, that's right, because we've switched access points, but both of these are on the same router, that means they're still in the same subnet, so your IP address hasn't changed. From the network layer, there's no mobility here. I think that's an important distinction. Does that make sense to you? Because the same IP address can be used by this computer regardless of which link layer access point he connects to. From the network layer, there's no mobility happening. So what's interesting is kind of depending on what level of the network stack you're looking at, you may have different definitions of mobility. Yeah?
So confusing.
So if we were to, so when would there be real mobility at the network layer? Right? According to what we just said, there wouldn't be mobility unless we had to go from one router to another router, one subnet to another subnet, and therefore needed to get a different IP address, an IP address associated with a different subnet. In that case, the network layer, right, that's mobility that affects the network layer, and if we wanted to support mobility, our network layer would have to be able to handle that. In the case of IP networks like this, I think that's not the case. It doesn't handle that. If you had TCP connections going and you switch your IP address, you had a broken TCP connection, you can't communicate anymore. You're going to have to run DHCP, get a new IP address, and then restart those TCP sessions. What this chapter talks about later is a solution to that called mobile IP, where mobile IP does allow you to keep your IP address as you move around to different subnets. Cell phone systems definitely have to handle that issue because you might go from one tower to the next tower to the next tower and actually need a different kind of network ID, and they, of course, have to handle that issue. A couple of advanced capabilities, I think just two. I mentioned this last time. One is 802.11 can adapt the rate that it's sending so that it can achieve the bit error rate that it desires for a given signal-to-noise ratio. So if there's a lot of noise, then you need to send in a different way using a different physical layer. Basically, different physical layer modulation techniques have different bit error rates for a given SNR. So we can actually, the 802.11 card can adapt the rate that it's sending to the current noise so that it can still get through enough packets that the bit error rate's not too high. And there's kind of a little example of how you'd move up that graph, right, as your bit error rate, or as your signal to noise ratio is decreasing. And at some point you'd have to jump back down and use a lower modulation, a slower modulation technique so that you can still get packets through successfully. The last part here on advanced capabilities is power management. This is a simple idea, but it's really, really important as we become more and more battery dependent, right? Which is we need to consider the energy implications, the power implications of a network protocol. Because if you're just burning through your sending and receiving, that takes power to do that. And you're going to exhaust your battery, and nobody wants that. So the power management features that are built in that they're optional, but they could be used. Allows the node to tell the access point in a special message, basically, I'm going to go to sleep until the next beacon frame. If you need to send me something, hold it until after you send that next beacon frame. So in this case, the access point would kind of buffer any frames addressed to that node until after that time period at which the node would wake up. So it can basically, if the node could put itself to sleep and it doesn't have to waste energy sending and receiving packets. So not unlike the way, right, students might drift off in class and say, hey, if you're going to say something important, wake me up. Okay, good night. Right? That's the same kind of idea that's in 802.11 in order to conserve power. Any questions on this wireless stuff in 802.11 Wi-Fi? It is really important stuff, and we just scratched the surface here. You know 802.11 is like the dominant wireless link layer. So it is valuable for you to know this stuff, and I encourage you to look into it more deeply because it's if you're going to work on networks, you're going to be dealing with 802.11. Okay, very good.